Fractional harmonics and star polygons. The main harmonics that we have explored so far, the 6th, 5th, 4th, 3rd, and 2nd, have a depth of 1. An essential angle W is described in equation 6, seen here. And here are the values we've actually looked at so far for each of the harmonics, ranging from 0 up to square root of 3 for the second harmonic. Now, there are other harmonics that have a depth beyond 1, and let's see what they are. There are conical radius that can be found between the main harmonics, and they're called fractional harmonics. For an example, let's explore the fractional harmonic for 4.5, seen below, located between the 5th and 4th harmonic. It's best to convert this fractional harmonic to a mixed fraction, in this case 9/2, which describes our harmonic in terms of its harmonic h and the depth d. This can then be substituted into equation 7 to calculate the conical radius RTA for this fractional harmonic, which gives us a result here for a unit sphere of 1.257 approximately. And even though we are able to calculate its conical radius, we don't know if it has any significant geometric relevance or not. So let's do some geometric construction to see what this fractional harmonic looks like. Now I'll be demonstrating constructing the 9.5 harmonic. The conical radius has been set to the value calculated. That's a reference mark we'll start with. There's the first mark, the second mark, the third mark, the fourth mark. Now we're approaching the starting point into the second rotation. Make the fifth mark. Now the sixth mark, the seventh, eighth, and the ninth comes back to the starting point. And we divided the conics into 9 equal arc segments. Now I'm just going to add in the 9 additional conics to show the pattern on the sphere. So what you're going to see here is we're creating a 9-petal design on the top of the sphere. There's a 9-petal design. On the bottom of the sphere, it's a 9-sided polygon. And that is the 9/2 harmonic. Here's the top, side, and bottom view of the 9/2 harmonics we just constructed. Let me describe the construction steps that divided the conics into 9 equal arc segments in 2 rotations around the conics. This is a view of a plane that slices through the sphere and shows the conics on a plane with a planar radius of RP. And this is the first marking of the conical radius RTA from point 1 to point 2. Now we can see the additional marks as we move around the conics in 2 rotations and end up defining 9 equal arc segments that describe the 9 vertices of a star polygon with every second vertices connected, which is known as a 9/2 star polygon. This corresponds to the mixed fraction that represents the 9.5 fractional harmonic. And in general, every possible fractional harmonic defines a star polygon, with its parameters defined by the harmonic h and its depth d. The harmonic h defines the number of vertices of the star polygon, and its depth d defines the number of rotations that are required around the conics. And the depth also defines the sequence of connections between vertices, either every second vertices, every third, fourth, fifth, or sixth vertices, etc., depending on the mixed fraction that represents the fractional harmonic. Table 2 shows all of the possible fractional harmonics down to a depth of 6. There are actually an infinite number of fractional harmonics with even larger depths. However, not all combinations or mixed fractions of h and d are valid. The fractional harmonic must be in the range between 2 and 6. And some combinations resolve down to a fractional harmonic of a lower depth. And in addition, every fractional harmonic corresponds and defines a valid star polygon. Here are some other examples of fractional harmonics that can be constructed on a sphere. On the left, we have a 7/2 harmonic that's located between the 3rd and 4th harmonic. And on the right, we have a 7/3 harmonic that's located between the 2nd and 3rd harmonic. This is an 8/3 harmonic located between the 2nd and 3rd harmonics. On the left here, we have a 9/2 harmonic that's located between the 4th and 5th harmonic. On the right is a 9/4 harmonic located between the 2nd and 3rd harmonic. Here we have a 11/2 harmonic located between the 5th and 6th harmonic. Also shown a sequence of conical radius markings. Here we have a 16/3 harmonic located between the 5th and 6th harmonic. This is a 17/3 harmonic located between the 5th and 6th harmonic. And finally, we have a 23/4 harmonic also located between the 5th and 6th harmonic. There is another construction method that can be used to illustrate these fractional harmonics on a planar surface. To do so, we will slice through the sphere with a plane that contains the conics. This will result in defining a circle with a radius of the planar radius rp. We first start with calculating the conical radius rt from the fractional harmonic using equation 7, and then from that we can calculate the planar radius rp using EQ1 and EQ6. Once you have these values, you can now draw a circle on a plane by setting the compass to the planar radius rp to draw the circle. Then you can use a compass set to the conical radius rt and mark off segments around the circle. The values for h and d will indicate how many segments there are, indicated by h, and how many revolutions, d, around the circle are required. And the depth, d, will indicate the sequence to connect each of the vertices of the star polygon, every 2nd, 3rd, 4th, or 5th vertices, etc. So for example, let's take the 9/2 harmonic, and it would calculate as follows. As you see below, equation 7 would result in a conical radius RTA equal to 1.257 for a unit sphere, and the planar radius RP would compute to 0.978, again on a unit sphere. I'll show you an example. We start by drawing a circle with a planar radius of RP that we just calculated. Then we make a starting mark and use a compass that has been set to the conical radius RT that we have calculated, and use this to mark off arc segments around the conics. And after 2 rotations, we get back to the starting mark and have divided the conics into 9 equal arc segments that define the vertices of a 9/2 star polygon. We can now connect every second vertices to finish the construction of this star polygon. Here are a few more examples of the K-Star polygons that can be drawn on a plane based on the geometric properties of its associated fractional harmonic. And here's a diagram of the 5/2 star polygon, along with its planar and conical radius defined, as well as a sequence of connecting at vertices. In this case, every second vertices is connected. Here are a few more examples. Here's a 7/2 star polygon and 7/3 star polygon. Now we have the 9/2 star polygon in a 9/4 star polygon. And here is the 11/2 star polygon, the 11/3 star polygon, the 11/4 star polygon, and the 11/5 star polygon. Now let's take a closer look at some of the geometric properties of a few of these star polygons. We'll start with the pentagon/pentagram system, which I refer to as the system of 5. The base angle here is defined as pi over 10, or more generically pi over 2n, or 18 degrees in this case. The angles of this system can be derived as seen here, where the integers represent multiples of the base angle, pi over 10. Now, during a separate analysis of the ratios of the various line segments in this model, I came across an interesting ratio of sines of the base angle. And this was where the product of the even multiples of the base angle divided by the odd multiples of the base angle was equal to the square root of 5. A little more on this later. So now let's look at the system of 7, which consists of the heptagon and both versions of the 7-star polygon. Here the base angle is defined as pi over 2n, or pi over 14. The angles in the system are defined here in multiples of the base angle. And as we saw earlier, we have this interesting ratio of the sines of multiples of the base angle that is equal to the square root of 7. Well, now let's look at one more system. This is the system of 9, which consists of the nonagon, along with its various n-star polygons. Earlier we saw the n/2 and n/4 star polygons. What's new here is the n/3 star polygon, which consists of 3 separate equilateral triangles, as you can see here. The base angle for this system is pi over 18, or 10 degrees. And as we did earlier, the angles of the system of 9 are all multiples of the base angle, pi over 18. And we can also look at the ratios of sines, here being equal to the square root of 9, which resolves down to just 3. Now, more generically, this is a representation or formula for any K-star polygon that exists, which I found very interesting as well.